Whether our protection relays are electromechanical, solid state, or digital microprocessors, the protection and control schemes must be provided with the most reliable power supply possible. Typically, we will need 250 volts or 129 volts DC for tripping circuits, and much lower voltage, say 48 or 24 volts DC for relays and other protective devices. Even when the whole plant or substation is out flat black, we must still have power supply for protection circuits, communication, and breaker switching. Now, we'll be looking at features of protection power supplies in this videotape, beginning with the basis of any uninterruptible power supply, the storage battery. In order to produce, say, 129 volts, the battery bank will typically consist of 60 lead-acid cells connected in series. That is, 60 times 2.15 volts equals 129 volts. A nickel-cadmium battery would need, say, 108 cells, each of 1.2 volts, for the same job. The energy content of the battery, that is, the capacity, is expressed in ampere hours, AH. The installation is designed to meet the demand which will be placed on the battery for a specified number of hours when AC power is lost. Say 10 amps for 5 hours, that is 50 ampere hours. After that period of time, the battery voltage will have fallen below the minimum acceptable level to operate the equipment properly. If each cell has a capacity of 50 ampere hours, then the whole battery bank has the same capacity as they are in series. In order to increase the capacity to 100 AH, we would need to connect another similar set of cells in parallel. The precise ampere hour rating actually depends upon the discharge rate as shown by the manufacturer's curves. In order to maintain capacity, the battery is kept fully charged by continuous trickle charging up to the required voltage. We'll be looking at battery chargers in the next segment. The basic lead-acid cell consists of 2 lead plates immersed in a dilute solution of sulfuric acid. When fully charged, the voltage across the plates is a nominal 2.15 volts. We can keep charging and recharging the cell. The state of the positive plate will go back and forth between lead peroxide when fully charged and lead sulfate when discharged. Similarly, the negative plate alternates between pure lead and lead sulfate when discharged. The modern storage cell consists of many such pairs of plates connected in parallel. The plates are usually suspended from the top of the container or jar and kept from touching each other by porous plastic or rubber separators. In order to improve the life of the battery, the soft lead may be alloyed with antimony to harden the plate. This is often referred to as the lead-antimony battery. This type of battery is certainly more robust, but it demands very high charging current after many years of operation, say 10 to 15 years. A far better plate material is lead calcium, as used in most modern battery cells. The fully charged lead calcium cell produces 2.25 volts as against 2.15 volts for the lead antimony. In this case, for a nominal 129 volt battery, 58 cells are connected in series instead of 60 for lead antimony. In addition to adding strength to the plates, another advantage of the lead calcium cell is its low release of hydrogen. The basic battery chemical process produces hydrogen at the negative plate, and this may be released to atmosphere. Under certain conditions, hydrogen can be very explosive, and there have been instances of battery explosions. This is why the battery room must be well ventilated and maintained as a no-smoking area. Actually, a battery contains a lot of energy stored in a small volume. If you connect a short circuit across the battery terminals, inadvertently or otherwise, a large amount of energy will be released. As a result of very heavy current flow, the battery may boil. The connectors can get very hot, and a lot of vapor can be produced in a few milliseconds. On a smaller scale, the same thing can happen if the battery charging rate is set too high. The electrolyte may boil, and a lot of acidic fumes will be produced. In an attempt to reduce hazards due to the release of hydrogen, many modern batteries are fitted with sealed tops. Yet another type uses a non-liquid paste as an electrolyte. These are often called maintenance-free batteries, as there is no evaporation of water and therefore no need for continuous checking of electrolyte levels. This type of battery is often installed in unattended locations. On traditional batteries, a long-standing maintenance procedure is to check the specific gravity of each individual cell. As the battery loses its charge and the electrolyte turns into water, so its specific gravity falls close to 1. Measuring the specific gravity, Sg, of the electrolyte can give you a good indication of the relative state of charge. Generally speaking, a fully charged lead-acid cell should have an Sg of about 1.23. However, different types of batteries have different ranges of specific gravity, so be sure to check the tables for your particular installation. Here is a typical table of recommended specific gravity with correction for temperature and different levels of electrolyte in the cell. Note that as the electrolyte level falls, the specified Sg increases. Why is this? Well, the liquid level actually falls due to the evaporation of water only. The sulfuric acid content remains, so the electrolyte becomes stronger and indicates a higher Sg. The electrolyte level must be topped up from time to time by the addition of distilled water. The specific gravity in each cell of the battery should be the same, as the state of charge should be equal in all cells. This is an important check that will enable you to spot a faulty cell. Most manufacturers recommend that the Sg of all cells should be within 0.01 of each other. However, remember, this limit applies only to batteries that have been in service for some time. When first installed, many cells have unequal Sgs, which eventually stabilize after some months on float voltage and after a few discharges. A new battery requires several charge-recharge cycles before the plates become properly formed. Let's look at some possible reasons for unequal states of charge in each cell. One common problem is that the float voltage is too low due to inaccurate setting of the battery charger. The best way to set the float voltage is to use a digital voltmeter and record the voltage across each cell. A lead antimony cell should indicate between 2.10 and 2.15 volts across each cell. Lead calcium cells should be between 2.20 and 2.25 volts. If the cell voltages are lower than this, perhaps a simple charger adjustment will solve the problem. The individual cell voltages should be within 0.04 volts for a lead antimony cell and 0.08 volts for lead calcium. If the measured cell voltages are unequal, the problem may be in the intercell connections. These may have loosened with time and require retightening. Be very careful with the torque wrench and insulate as much of it as you can with rubber tape to minimize the possibility of accidentally shorting out cells. Sometimes in a 2 or 3 tier cell arrangement, the top cells become much warmer than the bottom ones. In the short term, this can show up as unequal cell voltages and the need for frequent water replacement in the top cells. In the long term, this can turn into a major problem, as heat greatly reduces battery life. We should take steps to improve the ventilation system. If after all of this checking, the difference between cells still exists, the battery must be subjected to the procedure called equalization. This process consists of raising the charging voltage and applying an overcharge to the battery for several hours. This should not be done too often, as it may damage the cells. The excess current may cause heating and evaporation of electrolyte. The gassing that goes along with this could dislodge some of the plate material, which then falls to the bottom of the cell. If enough of this material collects on the bottom, it may short out the cell. The frequency, duration, and voltage of equalization vary for lead calcium and lead antimony batteries. Consult the manufacturer's manual. If a quick equalize is needed, we will have to use a relatively high voltage. However, be sure to check that the equipment on the bus can withstand the higher voltage for an extended period. Remember, the DC bus usually operates at the charger float voltage, but some 129-volt equipment, for example, will not like 141 volts. Another factor in selecting the voltage is the length of supervision time required. During a fast equalize, the battery and the voltage should be frequently monitored to make sure that the battery isn't getting too hot or that the cells are not gassing excessively. Clearly, a slower, low-voltage equalize is preferable if conditions permit. After equalization is complete, check the readings of voltage, electrolyte level, and temperature. If a maintenance-free battery is installed, there is no need to worry about equalizing or specific gravity. We should, however, check occasionally to see that the manufacturer's recommended float voltage is being applied across each cell or group of cells, and that the jars are running cool. If the jars are clear, a visual inspection may give you some advance warning of trouble. The only sure way to check the battery condition is by load testing. However, you can only do this if you can take the battery out of service and run on a standby battery. The simplest form of load test is conducted by disconnecting the battery from the DC bus and the charger, then applying a measured load to run the battery down to, say, 1.75 volts per cell. Plot the fall in volts against time. Check your plotted graph of battery voltage versus time against the battery manufacturer's curve. There are a variety of load testers on the market. Most consist of carbon piles, which provide a resistive load. There are also some electronic load testers available that give a good indication of battery condition. One problem we should be aware of with lead-acid batteries is that of sulfation. If a battery's left for a long time without a float voltage applied, the battery may become completely discharged. If enough time goes by, the lead sulfate on the plates forms crystals that act as insulation and prevent further charging or discharging. To help identify this condition, the plates look shiny and brown, as if they were shellacked. Sometimes this problem can be cured by applying a higher and higher equalizing voltage until the sulfation layer starts to disappear. Now, this process should be carried out with the load disconnected and under close supervision. The disappearance of the insulating sulfated layer can happen very suddenly, and the cells will start boiling unless the voltage is immediately backed off. One major safety consideration you must remember: all lead-acid cells contain acid electrolyte, and acid burns. Even the maintenance-free battery can leak or vent acid if internal pressure becomes too high. This could happen during severe overcharging or shorting. However, most of the acid seen around batteries is the result of spills when the SG is being checked. If this is not wiped up, the acid can cause corrosion on the exposed intercell connectors and posts. All safety precautions must be observed when dealing with acid, such as wearing safety goggles and gloves. So far, we've been looking at the lead-acid battery, but there are other types. One of the most common alternatives is the nickel-cadmium or NiCad battery, which produces a nominal 1.2 volts per cell. In this battery, the electrolyte is an alkaline solution instead of acid. This means that the battery can be used at temperatures well below freezing. It also needs very little maintenance. The electrolyte doesn't enter into the chemical reaction, and as a result, electrolyte loss is very slow and there's very little gassing. With the NiCad, it is difficult to check its state of charge, as it maintains nearly constant voltage, from 100% charge all the way down to almost 0% charge. This means you're never quite sure if the battery will work for any length of time when you need it. On the other hand, the cells are usually so trouble-free that you can leave a NiCad installation on float for years with little or no maintenance. Unfortunately, we have to pay a price for this kind of quality. NiCads are many times more expensive than comparably sized lead-acid cells. We are all familiar with the disposable, small, dry type of battery as used in flashlights and so on. For computer equipment, the lithium battery is used because of its small size and long life. Okay, so much for batteries. We have spent some extra time on this apparently simple device because in our experience it often appears to be neglected. And after all, the battery is really the soul of our protection power supplies. For now, it's time to take a break. Please switch off the tape and review this material in your workbook. In practice, the battery charger supplies the DC load with the battery floating in parallel. The output DC voltage of the charger must be carefully controlled so as to not overcharge or undercharge the battery. Any failure of AC supply will cause the charger to shut down and the battery to feed the DC load without interruption. The DC bus is usually equipped with a low voltage alarm to warn us of any problem in the charger or if the battery is becoming discharged. In most installations, a ground fault detector is also connected to the DC bus. It is important that DC from the charger be well filtered with only a small amount of AC harmonic components. The DC should also be free of voltage spikes coming through from the AC side. Even with good filtering, the DC battery charging current may still contain some small AC component. This has the unfortunate effect of heating metallic conduits unless both positive and negative leads are run in the same conduit. Alternatively, separate leads can be run in PVC instead of metal. So let's now take a look at a typical SCR charger circuit. You'll remember that we discussed the switching and control capabilities of the silicon-controlled rectifier in an earlier videotape. This particular charger is a 48-volt, 50-amp rectifier running off 230 volts AC. The input breaker is set to trip on high DC output voltage so as to prevent overvoltage damage to the load. The input transformer has several taps for differing input voltages. An MOV, or metal oxide varistor, is connected across the secondary to act as a surge suppressor. The rectifier section of the charger consists of 2 SCRs and 2 diodes. In any half cycle, positive or negative, current flows through 1 SCR and 1 diode to achieve full wave rectification. The SCRs actually control the output of the charger. The control circuitry fires the SCRs at the correct point in the input AC waveform. When the SCRs are turned on, the bridge starts conducting and continues to conduct until the AC sine wave goes to 0 volts. It then turns off. To apply maximum voltage to the load, each SCR must be fired very early in every cycle. In fact, just as the waveform goes through 0 volts. Conversely, if we want to apply minimum voltage to the load, firing of the SCR must be delayed as late as possible. In order to provide this automatic control, the charger measures the DC voltage output. Adjustments can be made on the control panel to set up the charger as required. Let's look at these controls. The float adjust simply raises or lowers the auto set point of the charger output voltage during floating of the battery. If this were a lead calcium battery bank of 24 cells, we would set the float voltage at 2.25 volts per cell, or 54 volts. We would then check the battery to see that we did in fact have 2.25 volts across each cell. If not, we would need to adjust the charger to a slightly higher value in order to compensate for the voltage drop in the wiring between the charger and the battery. A large voltage drop would, however, point to a problem. Either the wiring is too small or the connections are loose. Of course, this problem will only be apparent when the charger is delivering current to the battery, as there will only be a voltage drop across a poor connection when some current is flowing. So remember to check this during a battery recharge. The auto manual switch allows us to select the control mode. The manual position essentially duplicates the float control, so allowing manual control of output voltage. Now let's look at the controls for the equalize mode. First, the equalize manual auto switch. By selecting the manual position, we can place the charger into the equalize mode at any time. The actual degree of overcharge can be set by this equalize adjustment knob, which actually raises the set point of the charger output voltage. With the selector switch in the auto position, the charger will switch to the equalize mode automatically. It may be programmed with a timer to go into action every week or month. The theory behind this is that without frequent equalizing, the battery will never be completely charged. Now let's take a look at the output slope adjustment. This charger output curve displays a negative slope, or droop. The charger voltage drops slightly as the output current increases. This allows paralleling of two similar chargers. They will share the load according to their respective droop characteristic. The charger with the steepest slope will pick up a smaller portion of any increased load, as the voltages must remain equal. If the chargers did not have a droop characteristic, they would tend to fight each other to control the load, with wild swings of current between one and the other. This charger also includes a current limit control. Its purpose is to prevent excess current flow. When the magnitude of output current reaches the set point, firing of the SCRs is delayed to cut back the voltage, which in turn reduces the current to the battery. We also have a soft start adjustment. Soft starting means that the charger has a time delay in its voltage control circuit. After an AC interruption, the charger slowly raises the output voltage. The reason for this is that after a major power failure, the battery may discharge and become quite flat. When the AC comes back on, the battery demands a very high current from the charger. If we did not reduce the charger voltage on startup, the current limiter may turn the charger off, and the battery would never be recharged. Okay, so that is a typical SCR charger. I'm sure you'll find many of these units installed on your system. However, other installations may rely upon the ferro-resonant battery charger. The heart of the ferro-resonant charger is the ferro-resonant transformer, which was originally developed as a constant voltage regulator. This schematic shows the basic principle. The transformer has 3 windings. The input winding, which is loosely coupled to the resonant winding, which in turn is tightly coupled to the output winding. What exactly do we mean by the terms tightly or loosely coupled? Well, this refers to magnetic coupling. For tightly coupled windings, all flux, coupling one winding also couples the other. Then energy passes easily through the iron core flux path from one winding to the other. However, since the flux flows in 2 parallel paths, only a portion is coupled with this winding, which is therefore loosely coupled. This arrangement is often referred to as a magnetic shunt, since some flux is diverted through a second path. It's shown on diagrams by this symbol, indicating alternate flux paths. In the resonant winding, the inductance of the winding, together with the capacitance, forms a tuned or resonant circuit, which oscillates at 60 hertz. The energy required to maintain this oscillation is drawn from the loosely coupled input winding. The resonant oscillation produces a constant flux in that section of the iron core. Consequently, a constant voltage is induced into the output winding, which, remember, is tightly coupled. The result is a constant output voltage to the load, independent of variations in the input voltage. The ferro-resonant regulator does have limited regulation capability in both directions, about 10% maximum. But this type of regulator does have many advantages. There are no moving parts, such as bearings, or even active components, such as transistors. Therefore, reliability is very high. The ferro also has a small amount of energy storage, which may help ride through small voltage sags. Of course, there are some disadvantages. Ferros are heavy, acoustically noisy, somewhat inefficient, and the output waveform has about 10% distortion. However, all of these problems do not detract too much from its usefulness. When this regulator is used as a battery charger, additional controls are required. This schematic shows a standard 24-volt, 20-amp charger, which is typically used for communication equipment. This resonant circuit is controlled by the regulator, which monitors the charger's output voltage and current. The regulator also contains the controls and adjustments for auto or manual equalizing. All right, so far we've been looking at continuous DC supply. But we also need uninterruptible AC for certain items of equipment. We'll be looking at this in the next segment, but for now, please switch off the tape and study this material in your workbook. Battery chargers and batteries provide continuous DC power. Now let's take a look at the provision of uninterruptible AC power supplies, or UPS for short. If we add an inverter to the charger and battery, we can provide continuous or nearly continuous AC power to feed critical AC loads. The inverter is basically a transistor oscillator running at 60 hertz. It takes DC from the battery and produces an alternating waveform, usually a 60 hertz square wave. A more advanced type of inverter reproduces an AC sine wave from a large number of DC pulses that vary in amplitude and width. Each small voltage pulse is carefully controlled in width and height to reproduce the envelope of the 60 hertz waveform. In some units, the pulse width is increased enough to produce a stepped wave. This is then passed through the pulse width modulation filter, where the rough waveform is smoothed out. This block diagram shows the simplest and least expensive UPS, the offline system. When the UPS senses an AC power failure, it switches its output to the inverter that runs off the battery. The transfer from AC mains to inverter may take a few milliseconds, and this short interruption may not be acceptable for certain applications. Actually, most computer power supplies have a small amount of energy storage in the filter capacitors and may be able to ride through small interruptions. So this simple UPS system is quite adequate for non-critical installations. However, an improved system, known as the online UPS, provides more protection from power bumps. In normal operation, AC from the mains is passed through the ferro-resonant transformer to the critical AC load. At the same time, the battery is continuously charged through this winding. If the AC mains power fails, the charging circuit transfers to the inverter, and AC supply continues with the battery as source. This system relies upon energy storage in the ferro-resonant transformer to ride through the small power interruption until transfer to the inverter is complete. After AC power is lost, the capacitor and inductor in the resonant circuit continue to oscillate for a few cycles. The resultant flux supports voltage in the secondary winding for a short period of time. The key elements in this UPS system are the transfer switch and the control logic that operates it. The logic has to determine if there has actually been a power failure. This is not so easy. If a real power failure occurs, as the input AC voltage is just crossing over the zero line of its sine wave, the logic has to wait many milliseconds before it can determine that what it sees is actually a power failure. Then the transfer switch has to be thrown. And if this is an electromechanical switch, many more milliseconds can go by before the transfer is complete. The use of static switches employing SCRs will reduce this transfer time. Even so, up to a quarter cycle of the 60 hertz waveform, or 4 milliseconds, can still be lost. However, energy from the ferro-resonant transformer should help ride through this period with no more than a dip in voltage. In many installations, this is acceptable with this online UPS arrangement. There is every likelihood that important AC loads will continue to function. However, there is still some element of doubt, so if we have a really critical load, a military system or a main control system computer, for example, we may decide to go with the reverse transfer UPS, shown here. In this system, power flows from the AC mains through the charger, and then as DC to the inverter. AC from the inverter then passes on to the load. If the AC supply fails, the charger, of course, goes dead. But now, the battery starts supplying current to the inverter. There is no interruption whatsoever to the load. A disadvantage of this system is that the charger and inverter are operating continuously. Consequently, the unit runs hot, and reliability may suffer. A transfer switch is installed to permit the UPS to be bypassed for maintenance. A recent UPS development is the tri-port system, which is really an improved version of the online system, and similarly uses a ferro-resonant transformer. The tri-port name refers to the three interconnected systems: the battery and charger, the AC supply, and the AC output to critical loads. Each of these three systems is connected to one winding of a ferro-resonant transformer. Normally, AC power flows through from the utility into the ferro-resonant transformer. The power passes through the transformer to the secondary to supply the critical AC loads. Under normal operation, with AC power on, the charger continuously charges the battery and at the same time supplies DC to the inverter. This schematic shows a more detailed circuit diagram. The resonant circuit is actually connected to a fourth winding, which is closely coupled to the output winding. As long as AC power is being fed from the mains to the load, no power will flow from the inverter. However, when there is a power interruption on the main AC supply side, power flows from the battery through the inverter and the ferro-resonant transformer to the load. The smoothness of this transition is helped by the energy storage in the ferro-resonant circuit. At the same time, the AC line switch will open to separate the utility from the UPS. This is to prevent backfeed to other equipment connected to the AC panel. The UPS is generally sized just for the critical load and will not be capable of supplying any extra loads. Even where there are no other loads which could be backfed, there is always the possibility of a short circuit in the power feed. The output bypass switch is used to disconnect the UPS from the load in the event of a UPS failure. AC power will now feed directly to the critical loads with no backup. This can be achieved automatically as shown here by using fast-acting static switches using SCRs. The main advantage of the triport is that it provides for smooth transition from the mains AC power supply to UPS power, and it does this with very high efficiency. This system is also known as an interactive UPS. To help maintenance, some manufacturers provide a built-in fault finder. This usually consists of a mimic diagram of the system located on the front panel. By tracing through the lighted indicators on the diagram, we can diagnose which part of the system is giving trouble, and then follow the manufacturer's instructions for adjustment or module replacement. In practice, there are a few unusual failure modes which may not be discussed in your manuals. One fairly common problem is that the UPS keeps switching in and out. This can increase wear and tear on components and the station battery. The problem may be in the set point of the switchover voltage between AC mains and UPS. It may be set too high. For example, if your load can tolerate a 10% voltage drop, there is no point in setting your switchover point to 3%. Check the actual switchover voltage with an accurate voltmeter. Another source of problems relates to wiring of the AC supply. The main and bypass feeds must be run independently on separate cables and be of sufficient size. If this is not done, the voltage drop caused by the inrush when transfer takes place can abort the automatic transfer. Where ferro-resonant units are installed, another problem may be due to poor frequency regulation of the mains. In North America, this is uncommon, as our power system is usually stable within 0.5 hertz. But a non-interconnected standby generator can be another matter. Frequency swings of even a few hertz are capable of causing loss of regulation in ferros. The UPS should be taken out of the ferro mode for a minute or two during generator startup. We have described here several different UPS systems. You probably have several types of UPS installed throughout your power system. Make sure you become familiar with your own installations. Study the instruction manuals and company procedures. And now at this point, we all deserve a break. So please switch off the tape and thoroughly review this material in your workbook. One of the most troublesome parts of any electronic system is its power supply. This is because the power supply acts as the buffer between the hostile high-voltage AC system environment and the small, delicate chips on the printed circuit boards. Electronic devices run on DC and usually contain their own built-in power supply. Different DC voltage levels are required for different applications. Transistor circuits can handle only low-level DC, say 24 volts, to operate transistors and integrated circuits, while much higher DC voltages are needed to operate things like television picture tubes. For electronic devices, it is essential that the DC power supply be clean, that is, well smoothed and protected from voltage spikes. For this reason, the power supply conditioning includes filtering, voltage transformation, and regulation. The connecting leads are sometimes shielded to prevent interference. You will remember that we discussed this in an earlier videotape. The most common element in all power supply circuits is the transformer rectifier circuit. Typically, the transformer takes 120 volts AC and transforms this close to the required DC voltage level with due allowance for voltage drop through the rectifier and filter circuit. The full-wave diode bridge rectifies the AC and produces a rough DC waveform like this. This is then smoothed out by the filter capacitor. There are some not-so-obvious things we should go over in this circuit before looking into more complicated power supplies. The AC input is, as we said, 120 volts. But this 120-volt figure is RMS, or root mean square value. You'll remember that the RMS value of an AC sine wave gives us the equivalent action value as a DC voltage or current. If we looked at the AC on an oscilloscope, we would see that the voltage swings continuously between a positive peak of 170 volts through zero to a negative peak of 170 volts. The RMS value is 0.707 times the peak, that is 120 volts. Most portable voltmeters are calibrated to indicate the RMS value of an AC voltage. But the AC waveform has to be a sine wave for the calibration to remain valid. If you connect an inexpensive multimeter across the DC output of a rectifier bridge, it will read something like 0.637 of the peak rather than 0.707. The reason for this is that the meter is calibrated for a sine wave, but the converted DC is usually not a pure sine wave. This is good reason to use more suitable equipment, such as digital meters or scopes, when you're examining power supplies. Another sometimes overlooked effect is that of voltage drop across the rectifier diodes. For low voltage supplies, such as those used by microprocessors, this drop is significant. Depending on the magnitude of current, a diode can have between 0.3 and 1.4 volts dropped across it while it is conducting. The filter capacitor should be a computer-grade electrolytic, which means that it is polarized. It has to be installed with the positive and negative marked terminals correctly connected to the bridge output, or it will be destroyed. As much as 15% of the output from the rectifier may be harmonics, so the capacitor must work hard to filter out this AC component. Do not be surprised if it runs warm or even hot. Filter capacitor failure is one of the most common power supply problems. These capacitors are energy-absorbing devices. They run hot, and the electrolyte will eventually dry out and lose its insulating capability. The capacitor is also subject to stress from voltage spikes. To prevent this, you'll see small capacitors or other surge diverters, such as metal oxide varistors, connected on the secondary side of the transformer, like this. If you need to troubleshoot power supply circuits, particularly high voltage supplies, be aware of the charge on this capacitor. In most circuits, a low wattage, high ohmic resistor is connected across the filter capacitor to discharge it when the circuit is de-energized. If this bleeder resistor is not connected, the capacitor may hold its voltage for minutes or even hours. This can be quite dangerous to the unwary technician if the voltage is several thousand volts, as it is in TV circuits. It's good practice when working on power supplies to wear safety glasses. Also, use an ungrounded scope and never touch a circuit with both hands. This basic transformer rectifier circuit is simple, reliable, and inexpensive, but it suffers from one problem: lack of regulation. If the AC line voltage dips or rises, the DC output voltage also goes up and down, and this may affect operation of the equipment. As a solution, another stage is usually added: the regulator. In an earlier tape on static relays, we examined the shunt-type voltage regulator based on the Zener diode. This schematic shows another regulator, the series pass transistor type. All of the DC load current passes through the series-connected transistor. The voltage drop across this transistor is controlled by the signal which is applied to its base. The regulator's output voltage is compared with the set point, and the resultant signal is fed into the amplifier. The amplifier element, which may be another transistor or an integrated circuit, provides feedback to the base of the pass transistor. This in turn controls the volt drop across the transistor and consequently the voltage output to the load. As it is in series, the transistor carries full load current and can at times have a relatively high voltage across it. This means that it must dissipate many watts. And unless its heat sink and ventilation are good, the transistor will run hot, and we may experience frequent failures. As well, the amplifier and feedback loop use small voltages to control large currents. Interference voltages may get into the feedback circuit and cause major damage, including pass transistor failure. For example, operating a VHF radio near a series pass regulator could damage the pass transistor due to induced voltages. This may cause the supply output voltage to rise to an unacceptably high figure. Small capacitors, known as decoupling capacitors, are added to various parts of the circuit in an attempt to reduce this problem of interference. More drastic protection of the equipment against high overvoltage can be obtained by adding a protection circuit, such as the so-called crowbar shown here. The comparator chip senses the voltage on the output of the series pass regulator. When the voltage rises to the set point, the comparator triggers this silicon-controlled rectifier. As the SCR is now conducting, it effectively places a short circuit across the regulator, just as if we had placed a crowbar across the bus. As a result, the supply input fuse or breaker operates and shuts down the supply. However, this crowbar circuit is also subject to misoperation due to interference from VHF radios, for example. The same protective decoupling capacitors are needed, as we mentioned earlier, in order for this device to function effectively in a substation environment. A more recent development is the switching regulator. The basic circuit looks like this. Just as with the series pass circuit, the transistor is connected in series with the load, but the similarity ends here. The pulse generator repeatedly turns the pass transistor on and off, thus providing DC pulses at a very high rate. When these rapid-fire pulses are then passed through a filter circuit, they meld together to form what is effectively continuous DC. The switching is controlled by a feedback circuit, which responds to the output voltage level. To increase output voltage, increase the duty cycle. Then the transistor is on for longer than it is off, consequently increasing the pulse width. For less output voltage, the duty cycle is decreased. You'll remember we talked about pulse width modulation in the last segment. The switching transistor is sometimes applied directly to the incoming AC supply, say 120 volts AC, to produce alternating pulses at very high frequency, typically up to 200 kilohertz. These pulses are then passed through a transformer rectifier and subsequent filter circuit to provide controlled DC at the desired voltage. An advantage of the switching regulator is its small volume and weight. Because the pulse frequency is so high, the filter capacitor in the final smoothing circuit can be small and relatively inexpensive. Also, the high-frequency transformer is much smaller and lighter than the conventional 60 hertz transformer rectifier. This type of regulator has wide application in electronics, from the more exotic aerospace equipment to your home computer. So, in this videotape, we have examined various types of power supply used to energize protection and control schemes. We've looked at batteries and chargers, which supply a common DC bus. We also studied uninterruptible power supplies for critical AC circuits. And finally, we looked at individual power supplies for electronic devices. These are usually fed from the UPS critical AC bus. Please switch off the tape now and review this material in your workbook.